just after 4 in the morning, on the 28th of March 1979, in a control room on an island in the Susquehanna River, one small indicator light is telling a lie. The light says a relief valve on top of the reactor is closed. It is not closed. It is stuck wide open, and through it, the water that keeps the reactor core covered is draining steam and coolant into a tank in the basement below. The light is not broken. It is working exactly the way it was wired to work, and that is the whole problem. In our first episode, at Natanz, the screens read normal, while the centrifuges tore themselves apart. Here, the light reads closed, while the core begins to boil dry. Last time, we said this series would turn from the failures themselves to the systems built to catch them. The instruments, the indicators, the alarms. This is that episode. It asks a single question. What happens when the system meant to tell you the truth tells you a comfortable lie instead, and every trained instinct you have tells you to believe it? This is Failure Mode, Episode 5, 3 Mile Island, The Light That Lied. The plant sits on an island in the Susquehanna River near Middletown, Pennsylvania, about 10 miles from Harrisburg. There were 2 reactors. Unit 1 was undamaged that night and would keep running until 2019. This story is about Unit 2, a Babcock and Wilcox pressurized water reactor operated by Metropolitan Edison, running at about 97% power when it tripped. Unit 2 would never run again. The accepted verdict from the President's Commission and from the government's own Rogovin report is not that the machinery failed. The equipment, they concluded, was good enough that but for human failures, this would have been a minor incident. What failed was the picture the humans were given. The relief valve stuck open, and the one light that should have warned them showed the opposite. That light was doing exactly what it was wired to do. It reported the command sent to the valve, not the valve's true position, but no one in the room had a signal for what the valve was actually doing. The thesis of this episode is simple and uncomfortable. An indication system that shows you a reassuring lie is as dangerous as having no protection at all. Sometimes more so because you trust it. To understand the lie, you first have to understand the machine, as its designers did. A pressurized water reactor keeps its coolant, ordinary water, under enormous pressure, around 2,200 pounds per square inch. That pressure is deliberate. It stops the water in the reactor from boiling, even though it is far hotter than boiling water at the open air. The water stays liquid, and liquid water carries heat away from the core efficiently and predictably. Keep the core covered in liquid water, and it stays cool. Let it uncover, and the fuel overheats. Everything in this story comes back to that one rule. Controlling that pressure is a component called the pressurizer, a tall tank connected to the reactor coolant system. Unlike the rest of the system, the pressurizer is deliberately kept part full of water and part full of steam, a steam bubble sitting on top of a water level. By heating that water to make more steam or spraying it to condense steam, operators raise or lower system pressure. The steam bubble is a cushion. It is the thing they squeeze and release to hold pressure steady. On top of the pressurizer sits a relief valve, a pilot-operated relief valve, the PORV. Its job is protective. If pressure climbs too high, the valve opens and vents steam to bring pressure back down, then closes again. It is a safety device, a small automatic escape route for excess pressure. Under it sits a block valve, a second valve that can seal off the line entirely if the relief valve ever fails to reseat. Now, the 2 things you must hold in your mind, because both will be turned against the crew. The first is the pressurizer level gauge. Operators were trained to treat pressurizer level as their single most dependable measure of how much water was in the system. High level meant plenty of water. They were also drilled relentlessly, never to let the pressurizer go solid, never to let it fill completely with water, because once it fills, that steam bubble is gone and you lose the ability to control pressure at all. A solid pressurizer was, in their training, close to the worst place you could be. So they watched that level like a hawk, and they had a deep, trained reflex against ever letting it run too high. The second landmine is that indicator light for the relief valve. Here is the exact wiring, because it is the heart of everything. The light in the control room was not driven by any sensor watching the valve stem. There was no instrument measuring the valve's actual physical position. Instead, the light was driven by the electrical command signal sent to the valve's solenoid. When the control system energized the solenoid to open the valve, the light said, "Open." When it de-energized the solenoid to close the valve, the light said, "Closed." The light did not report what the valve was doing. It reported what the valve had been told to do. On a night when the valve obeyed its command, those were the same thing. On a night when it did not, they were opposites, and the crew had never been given a reason to distinguish the two. Follow the first 15 seconds carefully, because the order matters. It begins on the secondary side of the plant, the ordinary, non-nuclear side that turns heat into electricity. The main feed water pumps tripped. The accepted account traces it to moisture that had gotten into the instrument air system during maintenance on the condensate polishers. But the mechanism is a footnote. This was the trigger, not sabotage, and not a failure of any safety system. With feed water gone, the plant could no longer carry heat away on the secondary side. The turbine tripped. Heat piled up in the reactor coolant, and pressure began to climb. As pressure rose to around 2,255 pounds per square inch, the relief valve on the pressurizer opened, exactly as it was designed to do, to bleed off that pressure. A few seconds later, roughly 8 seconds after the pumps tripped, the reactor scrammed. Note the order. The relief valve opened first. The reactor shut down second. This is the reverse of how people instinctively tell the story, and getting it right matters. With the reactor shut down and the valve venting, pressure fell. As it dropped, at around 13 to 15 seconds in, the control system sent the electrical signal to close the relief valve. The solenoid de-energized. The command light in the control room changed to closed, and the crew, reasonably, read it as shut. It was not shut. The valve had stuck open mechanically. The close command was sent, the light obediently changed, but the valve stem never moved. What the crew now had was an open hole at the top of the reactor coolant system. A small break loss of coolant accident. Coolant escaping as steam through that stuck valve into a drain tank in the basement. And the one indicator that could have told them was telling them the opposite. Around 2 minutes in, as pressure kept falling, the emergency high-pressure injection fired automatically, pumping water back into the reactor to keep the core covered. The catch system worked. It came on by itself, exactly when it was supposed to. Remember that, because of what the crew did next. Here, the lie began to compound, and it did so through the crew's most trusted instrument. Pressurizer levels started to climb. To operators trained, that level is the truest measure of water in the system. Rising level meant one thing: plenty of water, too much if anything. But the level was rising for a reason no one in that room had been trained to expect. The stuck open relief valve was bleeding steam off the top of the pressurizer, and down in the reactor, the coolant was starting to boil. Steam voids were forming, and that expanding steam was pushing water up into the pressurizer, holding its level high, even as the total amount of water in the system fell. The gauge they trusted most was reading exactly backwards. Level was going up, while inventory was going down. Now put the two landmines together. The crew saw a pressurizer level climbing towards solid, the condition they had been drilled to fear above almost all others. And they had a relief valve indicator telling them the system was intact and closed. Acting on that picture, they throttled back the emergency high-pressure injection within the first several minutes, cutting the very flow of water that was keeping the core covered. This is the decisive worsening action of the accident. And it was not stupidity, and it was not negligence. Babcock and Wilcox had trained operators for a small break in the water space of the system. What they had was a break in the steam space, which behaves the opposite way. The crew applied a rule that was correct for the accident they had been taught, and wrong for the one they were in. They followed their training and their instruments precisely. Both misled them. And this exact failure had happened before. 18 months earlier, in September 1977, at the Davis-Besse plant, another Babcock and Wilcox reactor, a relief valve had stuck open in nearly the same way. Those operators diagnosed it in about 20 minutes. The engineers who understood the hazard existed, but there was no organized system in the industry for sharing operating experience between plants, and so the warning never reached the crew at 3 Mile Island. This is an organizational root cause. It is not proof that the crew had foreseen this and ignored it. They had never been told. Around them, the room was drowning. More than 100 alarms lit in the first minutes, with no prioritization to say which mattered. The event printer that logged what was happening fell hours behind. On one panel, a caution tag hung over a set of indicator lights, physically obscuring them. As conditions went saturated and boiling reached the coolant pumps, the pumps began to vibrate, pumping a froth of steam and water. Believing the vibration was damaging cavitation, the crew shut 2 pumps down around 1 hour 13 minutes in, and the last 2 around 1 hour 41, removing the forced circulation that was still moving water past the core. Uncovery accelerated. It was only when a fresh shift came in, looked at the temperature in the relief valve's tailpipe, still hot when it should have gone cold, and closed the downstream block valve at about 6:22 in the morning, roughly 2 hours and 20 minutes after it first stuck, that the hole was finally sealed. By then, the core was already uncovering. What actually happened next is not the story most people carry, and the difference is worth being precise about. With the top of the core uncovered around 100 minutes in, the fuel cladding overheated. Hot zirconium reacted with steam and generated hydrogen. Post-accident analysis, which could only be fully done once the vessel was defueled in the 1980s, estimated that roughly half the core, about 45%, melted, and that cladding on around 90% of the fuel rods failed. About 20 tons of molten fuel, corium, slumped down and pooled in the lower head of the reactor vessel. And then, the part the mythology gets wrong, the vessel held. The corium pooled in the bottom of that steel vessel and did not melt through it. Containment was not breached. The molten fuel never reached the environment. There was no China syndrome, no burning core, sinking into the earth. That is the single most important fact of this accident. A hydrogen bubble that formed in the vessel dome caused a national panic around the third day, a fear that it might explode. It could not. There was nowhere near enough oxygen present for an explosion to be physically possible. The fear rested on a flawed assumption, and the hydrogen was simply vented over the following days. The release to the outside was small, dominated by radioactive noble gases, mainly xenon. Very little iodine escaped, because it stayed dissolved in the plant's water. The average dose to the roughly 2 million people in the area was about 1 milligram above natural background, around 8 milligram within 10 miles, comparable to a chest X-ray, with a maximum plausible individual dose near 100 millirem, a fraction of what people receive from nature every year. There were no deaths and no injuries from the accident, and more than a dozen major studies over the following decades found no attributable excess cancers. This is not Chernobyl, and it is not the film The China Syndrome, which had opened in cinemas just 12 days before the accident, by coincidence, and depicted a very different, fictional disaster. Through all of it, the crew flew blind. The true state of the core was not seen until a camera was lowered into the vessel in 1982. The lesson of 3 Mile Island is the lesson of this whole series, and the fixers went straight to it. If the systems built to catch a failure can lie to you, then you rebuild them to tell the truth. Start with the literal fix. The regulatory requirement that followed, New Reg 0737, mandated positive, actual position indication for these valves in control rooms. In plain terms, replace the light that shows the command with a light that shows the valve. Where a plant had been reporting what a valve was told to do, it now had to report what the valve was actually doing. The single wire at the center of this accident was cut and rewired to reality. Then the wider net. Every control room got a safety parameter display system, a compact, reliable readout of the plant's actual safety status, so no one would again have to assemble the truth from 100 scattered gauges under 100 alarms. Emergency procedures were rebuilt from event-based to symptom-based. Instead of first diagnosing which accident you were in and then following that script, operators were taught to protect the critical safety functions directly, above all, to keep the core covered, regardless of diagnosis, so that a wrong diagnosis still defaults to a safe action. Control rooms were redesigned around human factors. Plant-specific full-scope simulators and far deeper training became the norm. And the industry created INPO, the Institute of Nuclear Power Operations, to share operating experience across every plant, so that the next Davis-Besse warning would actually travel. All of it circles the same point. The point Stuxnet made in a different decade with different intent. An instrument that reports the command instead of the reality is a lie waiting to happen. It does not matter whether it was wired that way by a 1970s design choice or forged that way by a piece of malware in 2010. The failure mode is the same. Pull the through line tight. At Natanz, the screens read normal, while the machines destroyed themselves. At 3 Mile Island, one light read closed, while the core boiled dry. In both, the operators were not blind. They were watching their instruments closely, and their instruments were lying with a straight face. That is the failure mode this series keeps returning to. It is not always a broken machine or a dramatic explosion. Sometimes it is a calm, truthful-looking display of a false reality and a room full of trained professionals doing exactly what that display tells them to do. The systems we build to catch failure are only as honest as the picture they show us. When that picture is a lie, every good decision made on top of it is wrong. That is what makes it so dangerous and so hard to see from the inside. We have looked now at how a plant meant to catch failure can mislead the very people trusting it. Next time, we stay with that question and follow it into a system where the people watching the screen were not misled by accident, but by design. If this kind of careful, sourced breakdown is what you want more of, subscribe and we will keep going, one failure mode at a time.